Hi, this is Ms. Stalberg. We are working on our thermochemistry problems. So let's start. We're in 2003, number 3, and we're on A. So if we look at that, let's start with A. We're finding the empirical formula. We are given the mass of carbon and the grams of hydrogen as well. So to find the empirical formula, we want to find the molar ratio between the two. In other words, we're looking for those subscripts. And so this is the mole to mole ratio between these two guys. So step one, get these guys to moles. So if we start with carbon, you have 6 grams, divide that by the molar mass to get 0.5 moles. For hydrogen, we're starting with 1.344 grams, dividing by the molar mass, and that gives us 1.33 moles of hydrogen. And so now we have the mole to mole ratio 0.5 to 1.33, but we know we have to put whole numbers here. So the next step is we're going to get at least one of them to a whole number. So if we divide both of these guys by the smallest, we get one of them to a whole number. This top one becomes 1, and it's a little bit easier to see what's going on. This guy becomes 2.6, repeating, 667. And so looking at that, I know I need whole numbers for both of them, not just one of them. So I need a number that I can multiply both of these by to get 2 whole numbers. And so now I'm going to multiply this by 3. And when I do that, I get carbon is in a ratio of 3 to, and when I multiply this guy, I get 8. And so we have C3H8. Let's move on to B. So the molar mass of the hydrocarbon is what we want now. We have the empirical formula, but we don't know the molecular formula to find the molar mass. And so if we look at the information we're given, temperature, pressure, and density, this is starting to smell like a gas law problem. And so if we look at that, since we don't have it changing temperatures or pressures, we want to go with PIV-NERT. In fact, we want to get molar mass somehow in PIV-NERT. And we can do that if we look at moles. And so we have pressure and volume equal. Instead of moles, we can do the mass in grams over the molar mass times R and T. And so when we do that, we can solve for that molar mass now. And so we get molar mass equals, and we have the mass times R and T over P and V. And now we have everything we need. And so let's keep going. Now, we have everything we need to plug in, but we're not given mass and volume. We're given density. And density has mass and volume in it. And so if we take this guy, density is mass divided by volume. And so you have to maybe notice this. And so let's go ahead and set that up. We know the molar mass equals the density times R and T over P. We get the density is 1.96. R is that gas law constant, 0.0821 or 2, around that. And then temperature. Now the temperature is not 25 degrees Celsius. We know this is a gas law problem, and so we have to get that guy to Kelvin. And so it is 298 Kelvin. And the pressure is 109. And so when we find the molar mass, we get 44. Excuse me. 44. And I think that's 0.01 or 0.1. And we have our molar mass. So now we want to know the molecular formula. And so if we take our empirical formula, we can try to figure out how does it compare to the molecular formula by looking at the molar mass. So the first thing we want to do is take that empirical formula and find what is the empirical formula mass to see the ratio between the two. And so if we have 3 carbons and we have 8 plus 8 hydrogens, we get 4. So the empirical formula mass is the molar mass. So the empirical formula is the molecular formula. And that molecular formula is C3H8. So moving on with this, we are in another experiment where we have heptane completely combusted. They give us the reaction. They give us the heat of combustion. So normally you have it written out here like this, but it's just written in the text of the problem. 4,850 kilojoules right here per mole, and that's for 1 mole. So it's per mole. And it says use the information in the table here to find the heat of formation for our heptane, our liquid heptane in that problem. And so if we look at that balanced chemical equation, we are going to use the heats of formation and calculate that. And so we know the delta H of any reaction equals the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. And so we are going to use that to solve this problem. And so we know this one, we know this guy. We are trying to find the delta HF of one of the reactants, but we know this delta H of reaction. So we're going to go ahead and put that in here, 4,850 kilojoules per mole for this one. Now that equals the products. And so let's look at the products. We have 7 CO2s. And if we look at our CO2s, those are 393.5. We also have 8 waters. And so if we look at the water is negative 285.8. So both of those, and then minus our reactants. And so our reactants are, we have the heptane. So this is our unknown. We are looking for the heat of formation of the C7H12. And there's only one of them, so we're going to multiply that guy by 1. The other thing we have are 11, I'm running out of room here, 11 oxygens. And oxygen's not in our table because any element in its standard state, its most common state, is 0. And so here is our entire reaction. So now we're going to solve for the heat of formation. So I'm just going to move this to the other side, move that to that side. And so I have the delta HF of our heptane equals, and so if I add all those guys up, and some of them are negative and this one becomes positive, I get 191 kilojoules per mole. And actually, with sig figs, because this guy is only to that tens place, this would be negative 190. Okay. Looking at part D, we have a small sample combusted in a bomb calorimeter, and we want to know the amount of heat released. And so we're trying to find Q. Now we're given the moles of the sample. We're given our combustion reaction up here and the delta H of that combustion reaction. So if we come over here and set this up, this is simply a dimensional analysis problem where we start with our 0.0108 moles of heptane. And that was 660, not 12 earlier. Okay, and divide that by the molar mass. And so the molar mass of this, so we have 1 mole of this giving us 4,850 kilojoules. And so if we know 1 mole gives us this much from our balanced chemical reaction, we know the heat produced in this reaction is 52 kilojoules. And this heat is released to the calorimeter. Okay. So let's move on. Actually, this is not E, this is part I and part II, part 2 of D. So this one we were going to skip, but I'll go ahead and work it for you. The total heat capacity of the calorimeter. So this is the amount based on the mass and the specific heat of the material of the calorimeter. And so to calculate this, this would be Q equals capital C times delta T to solve this problem. And we know the heat released by the combustion reaction is gained by the calorimeter. So we have 52.4 kilojoules absorbed by the calorimeter because the heat lost by this is the heat gained by the calorimeter, our law of conservation of energy. And so that equals the specific heat or the total heat capacity, which is 9.273 times the temperature change. And so solving for the temperature change, you get a temperature change of 5.65 degrees Celsius. And so that this problem will not be tested anymore. I was going to skip that in class, but I know you're probably curious since we didn't quite get there in class. So looking at number 3, we have hydrogen burning, and we want to find the standard enthalpy change. And so they give us the heat of formation for water, which is our clue that we're probably going to use the heat of formation formula. So I know the heat of the reaction equals the sum of the heats of formation of the products minus the sum of the heats of formation of the reactants. So using that, we can solve this problem. Now, looking at this, I don't know the heat of reaction. That's what I'm looking for. But I do know my product is water, and I have two of them. So 2 times my water, and our water is given right here. It's negative 285.8. And that's it. That's all of my products minus all of my reactants. And so if I look at my first reactant, I have 2 of them, and it's hydrogen. And hydrogen is an element by itself in nature, and this is how it's found. And so any element is going to be 0. It's an element in its gaseous state. And so is the oxygen. So we also have 1 times 0. So in other words, there's only one expression in this problem, and it's going to equal the delta H of reaction. And so the heat of reaction, delta H for that reaction, is negative 571.6 kilojoules per mole. So there is number A, 1 point for the setup and the answer. Part B, find the heat. So we're finding Q that is released when you burn 10 grams. And so if I'm given 10 grams and I know the delta H of reaction, I can set that up as a dimensional analysis problem. So if I have 10 grams of H2, and I'm going to know how much heat is released, if I know how many moles I have, I can figure out, I have the moles per reaction. And so if I can get this to moles, and so this is 2.02 grams for every 1 mole. Now looking at that reaction for hydrogen, for every 2 moles that react, this is what I produce in heat. And so for every 2 moles that react, I release 571.6 kilojoules. And so for this one, I get 1,420 kilojoules released. Now, technically it's released, and so you can put the negative, the released in the text of the problem does cover you. But that's our answer there. Okay. And our last part, part C, this was worth 2 points, 1 for setup, probably the setup for calculating moles, and then 1 for the correct answer. Part C, given the molar enthalpy of vaporization for water, what is the enthalpy change for this reaction? So it's pretty much the same reaction we have above, but the difference is this. And so this is kind of a weird way to see Hess's law. So we have, instead of forming a gas as our product, up here we have it forming a liquid. And so we have some information right here for it forming a liquid, or that liquid forming a gas. So the molar heat of vaporization reaction is, and I'm just going to write it up here, water that's a liquid becoming water that's a gas. And we know that the delta H of that reaction is 44 kilojoules per mole. And so if we look at that, if we add these two guys together, they almost give us this reaction. We have to do one more thing. I have 2 liquid waters here. I need to cancel 2 liquid waters, and that's going to give me 2 gaseous waters. And so that matches this reaction. This is our desired reaction right here. And so if I double this, I have to double my delta H. Now I already have this one from a previous problem from part A. So from part A, I found the delta H of that top reaction was negative 571.6. So if I add those two guys together, I get negative 483.6 kilojoules. Now, I would probably put this down here so that they could tell where my work was. For you, I'm going to draw an arrow up there for you to finish. Okay. Happy studying. I will see you soon. Goodbye.